So we started off with Unit 1, Chapter 5, Chemical Formula Equations and Calculations, Part 1. We started off with, first of all, types of equations. We understood that equations can be divided into word equations or symbol equations. We understood that word equations are simply the name of reactants written on the left of the arrow and the name of the product written on the right of the arrow. And then chemical equations, which need to be balanced, we balance them with coefficients. Coefficients are usually written in front of the formula. These are those big numbers which are usually written in the same way. They're neither subscripts or superscripts. And what we need to remember, a couple of things, important things are there while balancing is that we need to balance the atoms on the left and the right of the equation. We do so by adjusting those coefficients, and we did many examples over here. And during balancing of equations, we do understand that we have to count the atoms on each side of the equation to balance them, and we keep doing that and keep changing the coefficients until and unless we come with equal answers on both sides. In order to do that, we summarized it with a few important tips. We work across the equation from left to right, checking one element after another. We keep on balancing element after element. But if an element appears in several places, we leave the element for the end. And we notice that sometimes the element is automatically sorted out, or we can balance that element in the end because once we have balanced everything, it's easier to balance the last one. Now, if you have a group of atoms like sulfate or something, sulfates, nitrates, phosphates, uh, which are unchanged on both sides, there is no reason why you go with individual elements and not the whole thing. So balancing group of atoms wholly on both sides actually saves a lot of time. Now, check everything at the end. Make sure you haven't changed something that you already have encountered. So, if you did, you will be probably winding up incorrectly. One most important thing, you can never change a formula. You cannot write numbers in between a formula. You cannot change the subscripts. You cannot change the position of parentheses as you wish to or as you please to. All you're allowed to do is to write big numbers in front of the formula as coefficients, and that's about it. A few more equations were balanced, and we also understood that we can use the half in terms of fractions, or we can use zero point 0.5 in terms of decimals that we can use apart from whole numbers. But if you really want to convert anything to whole number, you can double or triple your entire equation to get your answer. Doubling is the only thing that we do with this table. We usually don't need tripling because we don't go with anything except zero point 0.5. Now, we studied state symbols. We understood that there are a total of four state symbols that we use along with the equation next to the substance. The state symbol is written for which solids are represented as S, small s, liquid, small l, gases, small g, and aqueous solutions or solutions made in water, AQ. Now, how much of a substance really reacts in a chemical reaction? We need to understand this. And in order to understand this, we need to understand masses because not all the atoms weigh the same. Some atoms are heavier, some atoms are lighter, which actually brought us to relative atomic mass or AR. This is something that we covered back in chapter number 3. We do understand that atoms are amazingly small. Mass of hydrogen atom is given with so many zeros after the decimal point, which gives us the idea that we don't have a scale that can actually measure individual atoms. So what we do is that we actually try to measure them with a comparative or a relative scale. On that relative scale, our standard is carbon 12 isotope. So carbon 12 isotope distance is the standard. We call that scale carbon 12 scale as well. That is pretty simple because we use the whole numbers. For example, carbon 12 has 12 atoms, and if we take 1/12 of that atom, it would be equal to the mass of uh, hydrogen isotope 1, which is most common isotope. So the whole numbers are really easy to use, which makes us wind up at the definition. The relative atomic mass of an element is the weighted average mass of isotopes. We generally took all the naturally occurring stable isotopes and then we measured it on a scale of which carbon 12 atom or isotope has a mass of exactly 12. That's what the AR definition was going to be. We found some examples related to fluorine or neon for practice back in chapter 3. So this relates to that. And at that specific point, we stopped. So today we are supposed to start with relative formula math or MR. This term MR is actually generally covers many things. We use it for relative formula math as stated over the heading right there. We also use it for relative molecular masses, and we can use it for, though we don't generally do it that way, but we can use it for relative ionic masses. Now you must be thinking, why so many different names? Now let me clarify. This actually is a bigger, broader term which represents ionic compounds. This term represents all the molecules, and molecules are actually made by covalent bonding. This term is specifically used for ions. You must be thinking, what have we used for atoms? So for atoms, we have used AR. So if you go for this kind of wording, you have covered almost all of them. So sometimes we are going to use the term molecular mass, sometimes formula mass. Which term is more appropriate? If you take a look at the hint, you'd notice that the relative molecular mass terms only applies to substances that are present in the form of molecules, which are covalent compounds only. This would not cater the ionic compounds. However, relative formula mass is a bigger, broader term that covers ionic compounds, and since covalent compounds are also shown in formulae, so it covers those. Ions are also shown in formulae, it covers those. So relative formula mass is a bigger, broader term, and actually the right term for MR. That's why they have used it in the heading. And it's pretty simple. Relative formula mass or relative molecular mass is again the mass of a compound on the same carbon 12 scale. For example, water would have a mass of 18 on the same scale. And again, it has been compared with carbon 12 scale. How do we come up with this? Let's calculate it. Let's take a few examples and understand. Before we go with these examples, I'd like to quote a couple of my own. For example, let's go with NaCl. It's pretty easy. As soon as you look up Na in the periodic table, you'll find 23 written over there. As soon as you're going to look up Cl in the periodic table, you'll find 35.5. So it's pretty simple. Na plus Cl, 23 plus 35.5 is 58.5. That's how we do it. Now the book gave the example of water. Water is going to be what? We know H's are 1 and O is 16 in the periodic table, but since there are two atoms, so 1 into 2 plus 16 is just one atom, so let's keep it that way. If you want, you can multiply it by 1, but really that won't bring a difference. So it's 2 plus 16, which is equal to 18. So 18 is the mass of water. So that's how we can cover entire substances. Be it an ionic compound, covalent compound, it really does not matter. Notice another example over here at the bottom of the page, MgCO3. Relative atomic masses from the periodic table are already quoted over here. Carbon is 12, oxygen is 16, magnesium is 24. What do you think the relative formula mass or MR of MgCO3 would be? Again, as I've said earlier in these classes, if you have a calculator with you, you'll be pretty quick to answer my questions. So if you don't have the calculator, quickly grab one. Are you there?
Yeah. I'm doing it, sir.
Okay, if you're taking your time to do the question, fine, go ahead.
Sir, for oxygen will as the mass number is 16 will multiply by 3, right? Because
Right. Perfect.
84.
84. Let's see if your answer has been correct all along. So there you go. 84. Are we good?
Yeah.
Now let's go something that consists of a bracket. Now you have CaOH twice, and let me tell you the bracket and the number below the bracket is multiplied for all of these. So
Mhm.
if you have this, the mass would be oxygen, two oxygen atoms. It's one calcium atom, two oxygen atoms, and two hydrogen atoms. That's how you're going to calculate it. Go ahead
So
and calculate
whatever,
it.
so sir,
Sorry.
whatever the mass will be, so we'll multiply by the number, right?
Right.
Okay.
So we are actually going towards more complicated examples since you are supposed to know and be able to solve the examples that consist parenthesis brackets. Moving on, I'll make sure that we go with some examples that consist of dots in formulae that you don't have a problem uh, facing any kind of substance and calculating its MR.
Sir, 74.
74. Let's take a look. Seems about right, but let's take a look. Are we good?
Yeah.
74. Now, moving up next, Cu is the 4.5H2O. Now, yes. Now, in this case, actually, the salt copper sulfate has five water molecules actually attached to it. And this diagram gives us a very good idea how water molecules are attached to it. So what we do is that we put a dot right inside the formula and we separate the water molecules from the formula. If you need to know what this water is, remember this water is that crystallizes out. If it is heated too much, we call it water of crystallization. 5H2O is water of crystallization. This water is actually necessary to form the crystals of copper 2 sulfate. If you take this water out, copper sulfate becomes white. If you add this water back in, copper sulfate becomes blue. They literally change their colors with the water of crystallization and without. So this water of crystallization is important. Remember, five water molecules are attached to only one molecule of CuSO4. So that's how we write it. With water, we call it hydrated salt. Without water, we use the word anhydrous salt, okay, which we are also going to cover in the upcoming chapters, probably unit 2. So if you are going to use the periodic table, remember to use the right number, mass number, which you have already stated. Now, what are you supposed to do during this calculation? I'll make it very easy. During this calculation, this dot means plus. So take this side, dot means plus, add both the masses, and you'll get it. Now, in order to make it more simpler, you have already calculated water to be 18. So do not calculate it as a whole. If you want to, let me tell you, there is one copper atom, there is one sulfur atom, there are four oxygen atoms, then added to it, there are 10 hydrogen atoms. This 5 would be multiplied by this 2, this 5 would be multiplied by this 1, and plus there are 5 additional oxygen atoms. So that's how we do it. Okay. If you want to do it smart way, 5 into 18, the mass of water. You already know the mass of water is 18, so 5 multiplied by 18. You don't necessarily need to do this. This makes the whole step easier for you. You can either pick this way or this way, whatever you like. Go ahead and calculate the mass for copper sulfate hydrated crystal.
Yes, you're done.
And the answer to this is
Uh, two 257.5.
257.5.
Yeah.
Seems like a little bit more than it should be. Okay, let me
Uh,
show you. It's approximately 249.5, and there you go. It's 249.5. Might have made a mistake at any point.
63.5 plus 32.
63.5 plus 32 plus 4 oxygen molecules plus 5 water molecules. There you go, 249.5. Pretty easy.
But sir, after water molecules, there is again oxygen, right? Five oxygen.
No, no, there is no oxygen after those water molecules. That
Okay,
is a
so
part of water molecule. Okay, let me tell you this H2O is entirely water. H2 is the
oh,
formula for hydrogen. H2O is the entire formula for oxygen. So this oxygen is not separate. This is a part of 5H2O. All right. You might have
yeah.
added that oxygen, and because of this, you have the whole calculations incorrect. Now look at this hint right over here. It is dangerous to calculate the number of hydrogens and oxygens separately. The common mistake is that we work out 10 hydrogens correctly, but then we count only one oxygen rather than five oxygens. So we make a big mistake. Or instead, in your case, you counted them six oxygen instead of five. So you again made a mistake. So it's better to calculate 5 into 18. That's the best way to do it. Make sense?
Yeah.
Okay, I don't think this example is good enough. Let's calculate the mass of Na2CO3.10H2O written right over here. And then MgCl2.6H2O. Go ahead. Do them one by one. You need more practice for these. Answer to Na2CO3.10H2O is
286.
286. Perfect. So sodium was 23, carbon was 12, oxygen was 16, the entire water molecules were 18. So it seems like a right answer. Okay, let's move on to the second one.
Sir, I'm still doing this one.
Sure, take your time. Yes,
It's 206, 203, sorry.
2 or 3. So understanding calcium, magnesium was taken as 24, chlorine as 35.5, and the entire water to be 18. Sounds about right. This would be 71 because there are two atoms, then 24, the
Yeah.
total should be 95, and the whole thing should be 106, 106 and 95. Sounds about right. Okay. So you may recheck these later, but let me give you another example. And this time I'm gonna switch it up a little bit. Okay, let's say you have 2 moles of Al2SO4 tri. What if you have this big 2 over here? How would you calculate it then? Do you know what this big 2 before the number means during calculation?
Pearson?
What you can do is you can calculate simply this and multiply the whole 2 with it, or you can calculate it this way, that there are 4 Al atoms, and then this 1 is multiplied by this 3 and then this 2. So 1 into 3 into 2s, and then 4 into 3 into 2O. So there are 6 sulfur and there are 24 oxygen atoms. That's how it goes. It's not 240, it's 24 oxygen atoms.
Okay.
So you can work it both ways, like this or like this. I just wanted to make sure that you have the proper concept of it, the idea of it, that how many atoms are there. So it isn't a problem for you when you're calculating it. Either way.
Mhm.
So this one is
So I used the first method and I got 692.
692. Okay, that means the individual one must be 346. Sounds about right. 96 into 3 is equal to 288 plus 54. That is, yeah, around 46 something. Okay, that's right. 692 seems about right. Okay, I'm gonna leave you with a homework example. You may note it down. Don't do it right away, but you can note it down. This is K2SO4 dot Al2SO4 tri dot 24H2O. It's a salt that we commonly use in lab for titration purposes, commonly known as Mohawk salt. So the math for 1 mole of Mohawk salt would be the calculation of all of these, adding
Mhm.
together, of course. And you're done writing the example, let me know so that I can erase it and move forward.
Good.
Okay, good. Erase this, let's move forward. Now, percentage composition, our next part. We are going to use relative formulae and we're going to calculate the percentage composition. You're familiar with the word percentage. We take the parts out of 100 parts. Composition means what it's made up of. Now we're going to use relative formula math and we're going to find by math how much of anything is a part of the whole compound. For example, a compound is copper oxide. And what if we need to find out what is the percentage of copper in this compound? What do? We calculate the MR, we take the mass of copper over the mass of whole compound, and we multiply it by 100. So it's pretty easy. Whichever element we need to find the percentage of, so the percentage of element is mass of element in that compound. It can be one atom, and it can be two atoms, it can be 10 atoms, it can be anything. And the MR of compound, all right, and we multiply it by 100 to get the answer in percentage. That's what we did right there. I hope you get the example,
Yeah.
right?
Yeah.
Now, he has also tried to calculate the mass of oxygen in sodium carbonate. So the MR is 106. Why don't we go ahead and finish this example up? Find out
Right.
how much oxygen is in percentage by mass present in sodium carbonate in a 2CO3.
Okay.
Remember that to find the element mass in a compound, take the whole part of the element. This is O3. This O3 is calculated right over here. So take this, take this part of an element divided by the whole, which is this. You'll get your answer, multiplying it by 100.
So, sir, whatever element they're asking, we will just take for that one and the total one, right?
And the total, MR, right? And that element may be 2 atoms, 4 atoms, 5 atoms. You need to take that many number of atoms as present in the formula.
So we'll plus them, right?
Yeah, we'll add them, of course. You multiply them, you add them, it's really up to you because the answer in both cases is the same. You add 16 three times or you multiply 16 by 3, either way it's right. It's math.
Sir, done. I got 45.28.
You must have gotten 48 over 106 multiplied by 100, and the answer comes out to be 45.28. Four significant figures are good. If you want to round it off to 45.3, that would be also fine. It's up to you. Three significant figures, at least there should be three significant figures. Four is also fine, right?
All right.
Trying to go for more is like wasting time. Trying to go for less, you don't get enough marks for it. Okay, let's
Yeah.
see if we have any more examples right after this one. No, they don't have any examples, and I'd like to give some of mine. Okay, now try to find out the percentage of oxygen in MgSO4.7H2O.
I'm not sure if I can do this one, but I'll try.
Sure, take your time. What do you say the answer is? The percentage of oxygen?
The answer is 32.52.
32.5. Okay, I assume that you took these four oxygen atoms out of here and these seven oxygen atoms out of here. So 11 into 16 over this entire sum. And the MR of this is probably 246. Am I right?
Yeah.
Okay, so this is probably 246. So that is multiplied by 100. So 11 into 16 was probably 176, right? So 176 over 246. This should be a much different answer.
That's different. Yeah.
So the answer is
Sir, the correct answer is 71.54.
71.54. There you go. I hope now you know. Now, the student tend to make the mistake of not taking seven oxygen atom or taking this one as four and this one as a fifth oxygen atom. That would be a big mistake. We have four oxygen atoms over here, seven over here. Adding them all up, they become 11 because 4 plus 7 is equal to 11, right? Okay, there is a very famous, actually, I would say infamous Cambridge question related to this one, and which is related to the upcoming chapters, by the way, gases in atmosphere, but I'm going to quote it over here, which write this question as a homework. You will love doing it as a part of the homework because it is all percentage composition, but it is presented differently. Which of these nitrogenous fertilizer is best to use based on the fact that it contains highest percentage of nitrogen by mass. A, NH4NO3, B, NH2 twice CO, C, NH4 twice SO4, and finally D, NH4 twice HPO4. So these are all nitrogenous fertilizers. We use them as nutrients for plants, as food for plants, especially for our crops. Now, which one is best to use based on the fact that we are that it contains the highest percentage composition of nitrogen by mass? It's a very simple question. You calculate the nitrogen percentage composition by mass for all of these compounds. The highest one is your correct answer. As soon as you're done writing, let me know.
Yeah, done.
And we'll discuss the answer in the next sitting.
All right.
All right?
Yeah.
Okay. Let's clear this. Okay. So this is 45.3, the previous one. I guess we have already checked it, right?
Yeah.
Okay. Then comes an entirely different topic, mole, and its different formulas. We'll have many upcoming formulas. I this